All right, so we talked last time about the velocity vectors and force diagrams you would see on the soccer ball at each of those points. And we kind of went to the next page and started talking about let's turn this conceptual idea into applying it to our math. So we start with the fact that some of these equations that we have, our equation toolbox, can be applied in either the vertical or horizontal direction. The vertical direction we saw from the front side, the ball or object accelerates in the vertical direction. In the horizontal direction, we see that the object or the ball moves at a constant velocity. So horizontally, there is no acceleration. So it's not that we're coming up with new equations, but seeing where each of our equations apply. The first one I'll leave for later, but the second one, we have acceleration inherently in that equation, so it's assuming that the acceleration is not zero. If it was zero, this term would cancel out, and it would just be your final velocity equals to your initial, and that would mean constant velocity. So this equation right here is going to go to that vertical side since that's the way the acceleration is, or the direction that the acceleration is in. The next equation again has acceleration, assuming that you have an acceleration that is non-zero. That will apply. If it was zero, this term would drop out, and you could still use that, but that looks a lot like the equation above. The first equation. So this one will say is to our vertical side. The next one, even though you don't see acceleration, the fact that you have a VF and a V naught is telling us that there is a difference in those velocities, so it's assuming that you are accelerating. So that will also go on the vertical side. Same with the next one, we have acceleration. Acceleration due to our Earth is negative 9.8 meters per second, and the force of gravity is vertically. And if we have acceleration, Newton's second law also will apply. Frictional forces, we tend to ignore air resistance, so this equation probably does not apply to us at this point, although it still could be used in some factor. As far as the horizontal velocities, this one, if we assume that we're not talking about an average, because average implies, again, that those velocities were changing, that really could go to either, but more applicable to our horizontal velocity. So if we just look at velocity is equal to displacement over change in time, that's also the same thing as saying if we rearrange it, velocity times delta t equals displacement. If we take a look at the third equation and assume that acceleration was zero, meaning no acceleration or constant velocity, that equation is the exact same as what you see here. So it applies to this horizontal factor, but really we don't rewrite the whole thing because we would be dropping out that term anyways, and this is just our original equation. The same thing goes for this one. This would be like a 2v because our velocities are the same. 2v times delta t times 1/2 is the same thing as saying delta t times v equals delta x. So that's giving us that same equation right there. This one, if the acceleration term were zero, again our velocities are just equal the whole time, and so on and so on. Acceleration due to Earth, not in the same direction as this horizontal way. So if we take a look at what we do with those equations, something to point out, we actually talk about them a little bit differently in the vertical direction. It's still the same equation, but we like to put subscripts on everything to describe what we're actually talking about. So in the horizontal direction, we really want to make sure we're talking about things that are horizontal. So x implies the horizontal variable for position, and the velocity is often used with subscript x to talk about the horizontal velocity of an object. On the right side now, that kind of changes our things because we have all of these equations have or the ones that have x in it, their delta x is implying that horizontal position. So I'm going to look at this third one first. This third one, instead of delta x, we would write delta y to imply that it's the vertical direction is equal to v naught y times delta t, time doesn't have a direction, plus 1/2 a delta t squared. Acceleration, you could also put a y after it to imply that it's the acceleration in the y direction. But for these examples that we're doing with projectiles, we don't have acceleration in the horizontal direction, so oftentimes people leave that off. The more important one is probably the v naught y to imply that you're talking about velocity in the y direction versus the velocity in the x direction, or velocity in the vertical direction as opposed to the horizontal direction. So I could rewrite each of these equations and just add in those subscripts. Vfy equals a delta t plus v naught y, and get a y there if we wanted to. Delta y equals 1/2 delta t times vfy plus v naught y. Vfy squared equals 2a delta y plus v naught y squared. And these have no implication with x already, so therefore they're kind of as is. So really, hopefully you realize that these are the same equations. It's just we're specifying a little bit further the direction of the velocity, and our displacement is now talking about vertical displacement, whereas this one is talking about horizontal displacement. But really, if I were to write these in words, displacement would be the same for both, meaning I could say displacement equals 1/2 a delta t times vf plus v naught, and you just know which direction the displacement is in. It only comes into play when we're writing it in symbols, because for us x and y actually mean something, so horizontal and vertical. Alright, so that's just an explanation of how we're going to use the equations. The bottom part is kind of how do we apply it to this situation where we know what we're doing, or so we know what we're doing with projectiles and how to solve for them mathematically. So some hints I would go with: always draw a picture or a diagram, and then complete an XY chart of your known variables. Then there are hints, and this is the XY chart. We'll talk about it in a second. For all projectiles, we know that the vertical acceleration is, so that's a sub y, negative 9.8 meters per second squared. We did that in our lab a couple of units ago. And then there are some key words. Horizontally launched projectiles, we know that the VYI, or V naught Y, is 0. And it's not something to memorize, but something to truly understand. We're talking about the vertical direction of the velocity, and if you're horizontally launching something, you're not giving it an initial vertical speed. You're not throwing it up or down if it's horizontally launched. So just to realize that. If launched upwards, the Vy at the peak of the path, and I'm really to describe that, I'm talking about something that's launched upwards. Here's the peak, falls down. The vertical velocity at that peak is 0 meters per second. So again, that's just kind of understanding that conceptual part about things as they are flying in the air. Then in the next case, for all projectiles launched at angles, so if we pretended this one was straight up or whatnot, but either way, launched at angles, we know that the total velocity v can be broken into two parts. So again, v with no subscript is talking about the resultant vector, and it can be broken into the vertical component and the horizontal component. So again, if we launch something with a velocity like that, you could have a horizontal component, so we call it Vx, and a vertical component, we would call that Vy. And in that case, it looks like that would be our initial velocity. The last hint there says, don't fool yourself. Vy, when the object hits the ground, is not 0. So what that means is you think something's falling, hits the ground, and stops. So after it stops, you're saying, well, it's not moving, so it's 0, but the velocity as it hits the ground is what you're talking about. Think about if you were to fall somewhere, you would feel like you were moving very fast as you hit the ground. So it's not 0. Sometimes people just assume that because the effects of hitting the ground make you come to a stop. But we're talking about as you hit the ground. All right, this XY chart that we have over here is really just to kind of talk about the pieces that we can look at. Notice time is not kind of divided between the two because the time is the same for both. If a projectile is in the air, it's moving horizontally and vertically, it's going to be in the air for the same amount of time, both vertically and horizontally. So once it starts and stops moving is the same time. So this is just kind of the same time throughout both. Meaning, when you go back to your equations, anytime you have delta t in here, you're using that same delta t on that side. Additionally, for the rest of these, we're kind of always looking at, well, what's happening? Acceleration is the next kind of easy one to look at. Acceleration vertically should be always negative 9.8 meters per second squared, and horizontally should be 0. For V0 and VF, this is going to be your components. So components, if you have things fired at angles. Or if it's just horizontal or vertical, you have to pay close attention as to how that projectile is fired. And then displacement, again, you're not going to necessarily have the same thing for your displacement horizontally as vertically. That always is kind of a common, a tough thing to say where they relate. Notice delta x and delta y. Sometimes the horizontal displacement is called the range. So just for a verbiage kind of lesson, range means the horizontal displacement. And then altitude or anything like that is talking about the vertical displacement. All right, so let's look at how we would apply this kind of technique. The question on the bottom says, a stone is thrown horizontally at 25 meters per second from the top of a cliff that is 45 meters high. So I'm going to draw my cliff. It's going to be 45 meters high, and the stone is being thrown horizontally, or the stone is being thrown horizontally. I don't know what I just said. So I'm just going to put it at the base of the cliff. We're not going to deal with the height of the person. We're just assuming that 45 meters is kind of accounting for it. I put the stone there and I show the horizontal velocity, and this is where I want to probably start filling in my XY chart. My initial, or my V0, my initial horizontal velocity is 25 meters per second. Because it's thrown horizontally, the vertical initial velocity is 0 meters per second. So we know that those two things are there. Its cliff is 45 meters high, and if we think about what happens with this projectile, it's going to fall down like that, some curve. So the height, the total height that this stone traveled was 45. That ends up being the stone's vertical displacement. How far it travels is delta x, its range. We don't know that yet. And let's see, we don't know anything about our VF for either. Acceleration horizontally is 0, and vertically is negative 9.8 meters per second squared. The time that it is in the air is unknown at this point and is asked in part A. So this is where we have to come through and see, like, well, what information do we have and what can we use, or which equations can we use to find the answer for that one? So because time is the same in both, you're either going to be using your horizontal equations and information, equation, and then your vertical equations and information. Because we have, let's see, we can go back up to this. Because if we were to look at our horizontal equation, that would be delta x equals Vx times delta t. We don't know delta x and we don't know t. So if I only have one of the three variables, I cannot solve for time. That's pointing us to using our vertical variables. We have the displacement, vertical displacement, initial vertical velocity, and we have the acceleration. We have 3, and each of those equations we were given has 4 variables. So if we have 3 of the 4, we can solve for time here. We know the time here, we know the time in the horizontal part as well. So let's take a look at the equations. the one that seems to work out is displacement equals v naught times delta t plus 1/2 at squared. So kind of this one with our y's rewritten there. So I'll take a second just to rewrite that one, and then we can solve. So delta y equals v y naught times delta t plus 1/2 at squared. Plug in those variables, or those numbers. Ooh, and this is a good point. Because the stone starts at a typical, to say it's starting at its own origin and it goes down, although the cliff is 45 meters high, the final minus initial gives us a negative 45 meter value. So negative 45 meters is our displacement vertically. The initial velocity is 0, which makes this whole term go to 0. So I'm just going to skip writing the t there. Plus 1/2 times negative 9.8 meters per second squared times time squared. To solve for t, we would have to divide both sides by 1/2 and then divide both sides by negative 9.8 and then square root. So if we see what we get there, time is equal to 3.03 seconds. We can now fill that into our table. You don't have to write it twice, but you can, or you can write it once, big, whatever you want. The next part of the question, which again, sometimes the people are more concerned with the range, which if we were just asking for the range, you would really have to find the time before you could solve the range. So kind of going through that process either way. But now it's asking for how far from the base of the cliff, which is asking the horizontal range or displacement, does the stone strike the ground at? And if we think about it, we can look at our one equation, which is delta x equals vx times delta t. We now have vx was given 25 meters per second. Our time we solved for above, 3.03 seconds. So our delta x is equal to 75.76 meters. So pretty simple compared to, in the sense that it's nothing new, we're still using our same equations. The key to success on these is really separating out your two variables, your horizontal variables and your vertical variables, and then still applying those to the kinematics that work for that certain situation. So again, horizontal, constant velocity, vertical, anything that is talking about acceleration. You can try the other questions in the packet as practice to kind of work through, or we will get to that in class. But see you soon. Bye.